Four, three, two, one, and that's just a guess, but I think we're on live on YouTube too. So quick round amongst the groups. We discussed to give about 5 minutes plus 2-3 minutes of discussion for each group to present their work. So first group is the one of Mohammed, I believe.
Yes. Can I share my screen? Yes. Okay.
You're allowed to.
Okay. Okay. Can you see my screen?
Yes, we can see it.
Okay. In this BrainHack, we conducted an exploratory analysis of personality-brain microstructure association. One of our motivation for this work is that last year and this year published 3 works that use a larger scale data for the association between the personality and structural of the brain. They use T1 data for computed thickness, surface area, or grammar volume of the brain, and interestingly, two of this work use human connectome project data. One of them report medium to large association, and one of them report weak association. Also, two last work that published in Neuroimage that use different data report weak association between structural of the brain and personality trait. For this, we use diffusion MRI data, diffusion MRI tractography for see the association between the 68 major fibers and diffusion measure of these fibers with personality trait test. In the first step, we did an exploratory analysis with linear regression analysis and use a tight p-value to find the fiber that associated with personality trait. In the first step, we see 3 fibers that 2 of them in limbic systems, and one of them is related to a brainstem that show associated with two subscale of the test. However, the association, is significant, but it's so weak, it's not so strong association. In the second step, we do sex differences analysis for female and male. However, in this step, we use a moderate type p-value, and we see that in the female for openness, for example, for openness to experience, we see, for example, in right-handed, we see some fibers that some of them is related, for example, with visual cortex, some of them related, for example, to limbic system, is show association. Also, in the left-handed, in the female, also we see that some fibers that it may be role that may be role in the openness. It's related to visual cortex pathway. Also, we have 2 fibers that two interhemispheric fibers, and one of them is middle cerebral peduncle, and one of them is a tapetum of the corpus callosum. That may be role in the connection of the left side fiber with right sided fibers. Also, we have found one fibers that in females that associated with neuroticism on facilicus in the female. This is a table for a female. Also for male, we see less fiber than the male. We see less fiber than male. We see in the right side, we see one fiber, and in the left we see two fibers that associated with neuroticism. Also see one fiber that is associated with consciousness in the male, and this is a table for male. Also, in the third step, we did an exploratory analysis. There is a new approach in diffusion MRI analysis that don't use the diffusion market. This analysis only used in the shape and the shape of the fiber. And for example, for each fiber, there are extract some feature that related to the shape of the fiber. It's not related to the diffusion.
Mohammed, 1 more minute, please.
Okay. This is yes, this is the last. And in this way, use this approach, we see a lot of result. However, because as I said, because this new approaches, it maybe need time to justify this result, and maybe to publish a paper about this result. For the next step, we need to again the analysis of a statistical test, and also use twin siblings data as a retest. Also, it may be helpful to create an study group to investigate neuropsychological and behavioral tests in human connectome project and other database using the tractography measure. Thank you so much for your attention. Okay, thank you.
Any questions or a suggestion or something to think about?
So basically, Mohammed, you found something, but it's not very robust, as I understood.
Yes. Also, we use a multiple regression and to find which feature is best explain our result. However, as I said, our result maybe prove that two last paper that justify that the structure of the brain is a weak association. I think as a result show that this, but yeah, but we see more fiber, more connectivity, for example. But as I said, it's weak association. It's not strong association. Yeah.
Yeah, you might check what resists in the other test sample with twins and siblings.
Yeah, yes, we use the twins as a retest. Yeah, yes.
Good luck. Thank you.
Thank you so much.
Thank you very much. Our next group is the one proposed by Patrick Friedrich. Anybody from his group, not only the proposer?
Okay. I think my group is also here. So I'm just gonna sharing my screen and start showing you guys what we found. So can you see the presentation?
Yes, we can.
Yes.
Awesome. So as I alluded during the first session, the idea here in our group was based on the fact that the standard space, this template shown here on the left, does not really capture or lose information of the individual. It's basically very well shown in, among other features, the shape of the motor hand cortex or hand knob, which may differ between individuals. So the focus of our working group was to work with the data in native space and see what we can do with it for different goals and aims. So one part of our group focused on labeling the motor hand cortex to basically label phenotypes of them in an open data set for future exploitation by means of machine learning approaches to automatize these phenotypes. Another part of our group, or another focus, was to see if we can actually correlate or predict handedness, left and right-handedness, based on the curvature of the central sulcus. And the last focus of our group was predicting the handedness or classification of left and right-handers based on the form of the presentinel gyrus itself. As I said again, all in native space. So it's really, for me, amazing to be a neuroscientist at this particular point in time, because there are so many open source data sets, and we use the IOMIC, the Amsterdam Open MRI collection for these preliminary results. In particular, the two separate data sets here, PIOP1 and PIOP2, because they didn't only have T1 images, but also a classification, a rudimentary classification of handedness in left, right, and ambidextrous participants. Onto the labels itself. We find something interesting here, because between the left hemispheric labeling and right hemispheric labeling, there appeared to be a difference in the difficulty. So what you're seeing here is the first data set depicted on the upper panel, the second data set depicted on the lower panel, and also split between left hemisphere and right hemisphere. If we're just looking at the first row or first column here for Susanne and for Lisa V, we find low inter-rater reliability in the labeling of the motor cortex, motor hand cortex. This is unsurprising because we were all not trained in how to identify these areas. However, what was somewhat surprising is that there seems to be a difference between the two hemispheres in the challenge it poses to agree on a label. So for both groups, the left hemisphere showed higher coherence or agreement than the right hemisphere, potentially indicating that the right hemisphere may be a little bit more difficult to put a label on. Second, we looked at the relationship between handedness and curvature. Just split handedness as nominal variable in right-handed and left-handed participants. And you see here the counts of our data and for the mean absolute curvature. In the right-handed participants and left-handed participant, segregated between left hemisphere and right hemisphere. And they seem to have somewhat similar variances. When we look at some statistical analysis, we first focus here on comparing right and left-handed. You see, regardless of the metric we're using, if it's the absolute or curvature, positive or negative curvature, there is no significant differences between left and right-handers. But there is significant differences between the left and right hemisphere, so that the curvature differs between the two hemispheres. Interesting enough, if we now look into some of the labels, just as a reminder, our labels are not final. They are not really, don't show a strong agreement. So we just look at labels for two of our raters now. And what we can find here is, regardless of the low agreement of the two raters or of the raters themselves, there appears to be a similar pattern in the variance depicted by the mean absolute curvature for the omega label, medial asymmetric epsilon label, lateral asymmetric epsilon label.
You have 1 minute, Pat.
Okay, I'm doing it quick now. So this was already quite interesting because if you compare left and right, it appears that there is some similarity in this variance. Last but not least, we characterized the PCG and tried to do a classification here. And for that, we used basically just the shape. We binarized these images and showed a low dimensional characterization, which I won't go too much into detail. But you can see here that we're quite well able to split the left from the right hemisphere. The left hemisphere indeed shows more variance between participants and the right hemisphere. Last but not least, handedness classification. We used a convoluted neural network with a 5-layer approach just to see if we are able to identify left and right-handers. And for this, we split the data into 70% as a training data set, 30% as a test data set. When you see here the accuracies against the epochs, the iterations that were needed, we see a maximum accuracy in the training data set of over 85%, just based on the native space morphometry we used here. So no really featured information besides the spatial anatomy. And this somewhat translates well also to the test accuracy or test data set. So for future research, we got to see if this result is somewhat replicable and generalizable. And with these all being said, I use my last -3 seconds to just say, it was such an amazing work. I thank all my amazing team members and thanks for joining me. It was really a pleasure. Thank you for organizing this whole, because without the organization team behind this BrainHack, nothing of this would have been possible. Thank you very much for your attention.
Thank you, Patrick. Other comments, questions?
I have a curiosity. Probably you already study this topic a lot, so you might answer. Do you think that a different morphology of M1 predict a better or a worse performance in like dexterity task or coordination task? So is there any evidence about this?
In all honesty,
You do.
no, I have no idea. I have no clue.
It would be interesting to investigate.
Preliminary research in that regard. And I was like, when we saw this result, the accuracies that really struck us, because there is so much research in the past about the neural correlates of handedness. Is it just that left or right-handers differ in the volumetry, for instance, of the motor cortex or the premotor areas, et cetera, et cetera? And in some relatively recent studies like Aucklandburg and one study of mine, 2016, other more recent studies, we found when you correct for multiple comparisons, volumetry does not differ between left and right-handers. So the neural correlate for handedness isn't that easy. However, this other angle, this machine learning based angle, gives us a way to investigate potential, not correlates, but potential information that can be drawn out of our data in order to classify participants as left and right-handers, which is really interesting. But I think I can't go into details about the relationship between conventional statistics and how we can draw inference from machine learning, because that would be like the whole 2 hours of just talking. So just to quicken it up, no, I didn't expect that. And I'm really, really curious to see if this actually generalizes and is a true finding or simply due to to overfitting of our data.
Mm-hmm.
So it will be cool to follow up.
As far as you know, is there continuous and non-binary hardness parameter that one can possibly use to normalize? Oh, very well.
Yeah, several.
Stunning.
So handedness shouldn't be seen as a binary feature of human beings, because we're not, like, I'm a right-handed person, but I also use my left hand for something. And one of the oldest used instruments here is the Edinburgh Handedness Inventory, which I don't know how many studies use this questionnaire, which basically gives you a laterality quotient, which indicates the strength of being right or left-handed. And we didn't have access to this kind of data, but it would certainly be interesting to see if we can do real predictions of these handedness scores based on the morphology of the precentral gyrus. And instead of just doing a simple classification into left and right-handers. So that's also something to look at in the future.
Thank you. So the next one is Umberto, Granciol groups.
Yes. Okay, I will share my screen. Okay. Okay. So in our working group, we try to analyze again and find an architecture and the relationships among human beings. Especially, we started with two aims: that is, replicating the results of the overall on the overall group of the previous study, but replicating on each gender and on each potential clinical and non-clinical subgroups. I have to spoil you that we managed to do the first aim, but not the second, because we saw a lot of interesting results in gender and completely absorbed us. In the day, especially in day 2 and 3, after finding a solution from a methodological point of view for the variables, we started to estimate the networks. Especially in day 2, we estimated the exploratory graph networks, and then in day 3, we converted such correlational model in Bayesian and causal pathways. I don't know if you remember, but this was the overall network, so 7 domains with 37 variables. With this, the correlation. The results we found in female group is very interesting because, first of all, we found that as for the overall group, the openness to experience created some problem. It was an unstable measure, such as anger aggressivity. But maybe the result that impressed us was the fact that the network for female participants has another dimension. It emerged a new dimension that we call well-being, and this is the one in red. That clusters measure all the measure of the database related to aspect referring to the well-being, that is self-efficacy, perception of stress, conscientiousness, perception of rejection, etc. While in sky blue, there are all the variables related to mental disorders. So anxiety, depression, withdrawal, pathological withdrawal, agreeableness, etc. And the red and the sky blue dots in the first group were in one single dimension. So the fact that impressed us was that in male, this new complex model was not confirmed. That is, in male we found the same dimensions of the overall group, with the differences that for the variable 38, that is openness to experience, it was very stable across male and inserted within the cognitive domain. While the tobacco consumption, we removed this variable because it was very unstable. So, and then the clusters were very, very similar to the overall group. So in a provocative way, and I asked to my female colleague to say this sentence, I have to say, we found that yes, females are more complex than men. And in fact, they are represented with separate domains, but strictly interrelated. While in men, everything is inside, everything is together without clear specification, I have to say. So I asked permission to say this. Then we found, we tried to analyze such results considering the previous literature, and we found that indeed the openness to experience is linked to a higher level of fluid reasoning and general cognitive capacity. And in fact, it is also related to the aspects of the so-called cognitive reserve. And that's why maybe we found that for males, especially, the V38, the variable 38, was inserted in the model, not excluded, as in the female one. While the problem of tobacco maybe is related to the idea of men smoking. So maybe the people, while asking to the questionnaire, were more prone to cover, not to cover their intentions. We found that also. I already saw the complexity. I would like to show you finally the results of the Bayesian network. This one, I don't know if you remember, was the original one, the overall one. In the female, we saw that something changed. That is, in this case, the well-being was influenced by the mental health, and it is. And the very interesting stuff is that we didn't a priori set such R, so it was completely new and estimated by the model. And we have, as usual, some outsiders, like again, sleep problems, or B29 that stands for anger and aggressivity. But for the other connection are still the same, that is externalizing a mental health, influencing the substance consumption and abuse, mental health and the cognitive function influencing responses to the delay discounting task. Such scenario is a little bit different between female and male participants. In fact, as you can see for the male participant, first of all, of course, there is not the dimension of number 8, but what is interesting is that in this case, mental health influences the cognitive functions.
Just for clarity, Umberto, is this males?
Yeah, is this male?
Oh, yeah, I'm sorry.
Okay.
I just forgot.
Okay, thank you.
Yeah, there's a typo, I'm sorry, but I had this result in the last few seconds before the presentation.
No problem.
And as for the female group, externalizing influence the mental health. So it is these are new results that confirm in some sense some theories, clinical theories, like the famous secondary problem, or having or not having an externalizing or internalizing problem. So concluding, the take-home message is the overall model is different between female and male, not only in terms of the architecture of the model, because we found that for female it is more complex than in men, but also in the way the domains influence each other, essentially, especially if you add another dimension. I really want to thank you for organizing and for inviting me for the first time, and I really want to thank the people working in the working group with me. They were very precious. And they also gave me a lot of hints and future direction and perspectives. So thank you very much.
Thank you. Good luck with the project.
Thank you, Umberto. I'm excited. I work with him on this project, on the initial project, and wow, I'm curious also what might be the reason of this separation in females between mental health and well-being, which is not present in males. So what might be the reason? like female have a higher resilience and tend to separate problems that could affect well-beings. So I really don't know. Do you have any idea of this pattern?
Beyond the stereotypical sentence I said some minutes ago, I still haven't.
Yeah.
I have to reason about it.
Are you also planning to understand how robust are these effects, maybe with another data set, or I don't know?
Yes.
Experiment.
Yeah, the idea is that one. The idea is to collect also other data sets with the same measures like the open source databases, and not only to validate in the same age range, but also considering other different ages.
Okay, thank you.
Really interesting, thank you. Next group, Marco Marino's group. Anybody from this group is here?
Yep, we are all here, I think. So I share my screen.
I confirm that we do see the screen and you and hear you.
Okay, you see the presentation now?
Yeah, we do.
Okay, that's great. Okay, well, so actually, first of all, I would like to thank actually the group. We have been working about this exploratory project actually, which was conceived, let's say, just last week, I would say, also thanks to the organizer of the BrainHack, who also suggested actually the database that we could use for doing this work. So thanks a lot for all the organization and for the work together with the group. So I will actually start the presentation, but another person will end in. So because we had a very big discussion on the whole topic, since no one had a true experience on it. So it was a very nice interaction with the whole group in these days, and I really enjoyed that. So thanks for that. So the idea basically about this art-brain interaction is that their interaction produces behavioral and mental changes, and especially studies shown that the heart rate variability links the heart and the brain. And this thing has been checked for several tasks and cognitive experiments, let's say, but very few is known about the resting state link with the heart rate variability. And so this is what we aim to do somehow, to explore which was the correlation with well-known resting state networks detected with the fMRI. And so to this end, we used the Lemon dataset that was suggested, which is composed by many participants, of course. We actually focus only on 10 of it in these days. So it is, of course, a very small number, but it was just a proof of principle, let's say. And in this database, anyway, the important thing is that we got the resting state fMRI data. So it was 15 minutes recording. And together with that, there was also the ECG signal, the cardiac signal recorded simultaneously. So together with that, not only the neuroimaging data were available, but also some cognitive battery tests and different behavioral scales that then we try to use somehow to correlate with some of our results. So to get the fMRI resting state networks, we implemented an approach based on independent component analysis, which was applied on the subject level, so individually for each subject. And this gave as an output a spatial pattern, which was associated with a brain network. In this case, for example, we could see something could be a default mode network, and a time course associated with it. So this one is actually the important thing that we are going to focus on this time course, because this one will be correlated with the cardiac signal, which of course cannot be used as it is. So here we see pre-processed ECG signal, and we can see clearly the peaks. So here basically we calculated the distance between one peak, one bit and the other. And this one was used for calculating the heart rate variability. And so once that we got this measure that was expressed in a bit per minute, we actually defined a kind of a dynamic approach based on windowing. And I would like also actually to thank Arianna for the suggestion from the project report of yesterday. And basically from here, in each window, we calculated the heart rate variability. And so we got some a kind of low fluctuation signal that then was correlated with the fMRI, which at the same time was also, windowed. And so we extracted the same measure of variability also for the fMRI. So at this point, we got some correlation for our 10 participants. And so here we can see each bar represents the average of each network. And we got two significant networks somehow, but we mainly focused on this one, which also showed a nice correlation, almost higher than 0.2, which actually corresponds to the ventral attention network that here you can see somehow. It includes the tempoparietal junction and the ventral frontal cortex. And here you can see the map extracted for two representative individuals. And so once that we got this information about the correlation, the interaction between the brain, let's say, and the heart, then we decided to check also for a possible behavioral correlates. And for this, I would ask the help of Elisa that can continue with the presentation here.
Right, so as Marco said, once we saw that ventral attention network was correlated to heart rate variability, we started to think among the behavioral tests that were taken from the subjects, we started to make an educated guess on which kind of scale would then correlate, be a behavioral correlation to this heart-brain interaction. We decided on the cognitive emotion regulation questionnaire and the straight trait anxiety inventory. I will, well, no, the one before. No. Basically, why did we think that emotion regulation would correlate to the ventral attention network activity? It's found that the ventral attention network reorients attention to salient stimuli, and Viviani suggests that attention is the key to achieving regulation. So it's emotion regulation is a very cognitive aspect which does involve the ventral attention network. So we thought it would correlate, and the state trait anxiety inventory we decided to use because an fMRI study with students who were stressed right before an exam period had a higher activation of the ventral attention network than those who did not. And in fact, we did find some correlation between these factors. In the cognitive emotion regulation questionnaire, we had a correlation of 0.56. Unfortunately, it wasn't significant. I think it was just below significant. It was 0.06, if I'm correct. And for anxiety, we had a slight negative correlation, but also it wasn't significant, but it was a start. So the take-home message kind of is that the ventral attention system results from the most relevant, the ventral attention network was the most relevantly correlated to heart rate variability. It is a network that is dedicated to the detection of unattended and behaviorally significant stimuli. So obviously it's also likely to be activated during resting state conditions. We also found that the amygdala, insula, and anterior cingulate cortex were shown to have a link with the heart rate variability. We saw this also with the MRI visualization of the data from the data set. And these areas.
Wrap up.
Sorry?
Please wrap up, because we don't have much time. Thank you.
So in conclusion, our results confirm that the information present in the literature between the heart rate variability and the brain regions is sound. And we added a link with behavioral aspects such as attention, emotion regulation, and anxiety. And we opened the road for further discussion. We propose a preliminary framework to combine fMRI resting state networks, heart rate variability information, and behavioral data to investigate mind-brain-body interaction.
Okay. Sure.
Great. You have some very encouraging results with only 10 subjects, if I understood correctly.
Yeah. We could only focus on 10. So
that is already very encouraging.
It was a bit exploratory, and we focused a bit on some literature for checking what could have been the behavioral scale most likely to be correlated with this information, and we were lucky maybe in this.
Marco, thank you for and all the groups, thank you for the talk. Can I become a reviewer too for a moment? So you show that the correlation was observed especially for auditory and the ventral attention networks, which include the regions that are in the lateral part of the brain. So in the more temporal and the parietal, but in the lateral part of the brain. So my question is, it is possible that the relationship depends on the position of the region in the brain, and so related to the artifact related to blood flow, rather than the functional meaning of these regions in relation to heart rate variability. So this was...
Yeah, it's actually a super good observation. I mean, and it is hard to say, of course. I mean, also the things that we got, I mean, they are nice, they are preliminary, but I mean, I wouldn't personally believe too much about that. Though we were encouraged by considering as reliable, let's say, or possible this option of this network, because actually we're checking the functional correlation of the heart rate variability with the whole brain that has been performed in previous studies. There was actually a significant correlation also in those regions. So let's say that was, how can I say, promising for us that those regions that were found to be correlated, they were actually belonging to the network that showed the highest significance.
Okay, thank you. No worry.
Okay, thank you.
One last observation. I might have missed it, but did you split state and trait anxiety?
Did we split?
We used just trait anxiety.
Trait, okay.
There was another behavioral measure for state, but we used just the trait one.
Thank you. Okay.
Marco, the last slide from our presentation is missing.
It's missing. It was an important one.
Yeah.
Okay. This one.
Right. It was just our conclusion about the BrainHack, about how it was a great interdisciplinary experience, and that although Marco basically is a genius for MATLAB and was really great at doing that, he did make us feel like we could make contributions with our limited knowledge, and we appreciate that.
Okay, well, thank you. It was a pleasure to be, to work with all of you, actually.
Thank you very much to this group. I want emotional support too, actually, and I would change it in trade of MATLAB. Okay, so our next group, Arianna Menard, this one.
Sure, I'm gonna start sharing my
Hi,
screen.
Arianna.
Hi, everyone. Okay, I hope you're able to see it. So my group focused on the decorrelation between graph theory measures and behavior from the ACP dataset. In particular, what we did was to extract measures from task fMRI data, in particularly looking at the 2-back working memory for faces and tools, from which we have looked at measure of accuracy and reaction times, both for the target and non-target stimuli, or non-target stimuli are simply stimuli that are novel in the presentation. And then we moved forward in extrapolating graph measures by means of an exploratory analysis, meaning that we started at the whole brain level, and then we narrow it down to looking simply at graph properties of the frontoparietal network, and then even more in depth looking at single node level for the regions forming the prefrontal cortex of the left hemisphere. At the whole brain level, we have been looked at very basic graph theory measures, which are the average characteristic path length, clustering coefficient, measures of efficiency for both the global and local level, and modularity. Whereas for the network level / single node level, we have measures at the node properties, especially between the centrality, the path length, clustering coefficient, and participation coefficient. I will not go into the depth of each measure, but just as a sort of spoiler of what we're actually going to focus on, I will mention between the centrality and participation coefficients, because those are where our results mainly focus on. So between the centrality is basically as a measure of centrality of our node, as it's the number of paths that cross a vertex. Whereas the participation coefficient tells us how much the node is involved in connections with other nodes of only zone community, or whether it has a lot of interactions and therefore paths that goes to nodes that actually belong to different communities in the brain. What we focused on in the first day was mainly to perform matrix thresholding. We know that in graph theory, this is a necessary step. So we looked at connection densities of our matrices ranging from the 10% to the 40%. So moving toward different degrees of thresholding. And then on the first day, we also looked at how we can extract graph theory measures and how we can plot them in the brain with nice software tools such as BrainHack Viewer and Gephi. On day 2, and 3, we digged into models and results, and those are what we could find. So basically, we couldn't find anything at the whole brain level, which I think it's pretty straightforward. But we did find something that was quite interesting, both at the network level for the frontoparietal and just looking also at the nodes for the lateral prefrontal cortex. For what concerns the frontoparietal network, what we observed was that the ability, the efficiency of our participants in performing phase target accuracy was significantly predicted by the between the centrality and the participation coefficients of the nodes of the frontoparietal network. Similarly, the reaction times also for stimuli as phases that were target, there was a significant prediction by the between the centrality of our nodes. And here is a sort of representation of our positive correlation. When we moved into looking at the single nodes, we have focused our attention on the nodes of the prefrontal cortex. So in particular, those 6 nodes represented here. The size represents the between the centrality of each of those nodes. And what we could find is that actually 2 of them, so vertex number 3 and 4, were actually able to significantly predict the reaction times for the detection of tool objects. And this is the prediction. For one of the nodes was positive, for the other node was instead negative. As a other result, what we observe is that the accuracy for faces was also predicted again by the participation coefficient of one vertex, mainly in the brain, in the prefrontal cortex. And here you can see the relationship. And secondly, we observed that, again, the accuracy for faces, but in this case, only for target faces. So the one that I showed before was just general, but this is specific for target faces, was predicted again by the participation coefficient of 2 vertices of the prefrontal cortex. So vertex number 1 and vertex number 4. And here you can see the relationship. So again, for the known target instead, we observed that vertex number 5 was predictive of phase accuracy for known target stimuli, again, in terms of its participation coefficient value. And this is the relationship. And finally, what we can conclude. So basically, our conclusions were mainly focused on looking at participation coefficient and between the centrality. And what is interesting, since we observed that the participation coefficient was positively associated with our results, it means that actually the participation of frontoparietal nodes to other communities is what matters. So this actually gives us the impression that inter-network interactions are very useful for describing working memory performance. This is generally because a participation coefficient of 0 tells us that the node is simply working with nodes of its own community, but higher levels of participation coefficients actually tell us that the node has a lot of paths going to any other nodes in the brain that do not belong to its own community. So I think this is interesting, and there are already evidences in the literature that show how the executive functions are actually represented by a diversity of networks in the brain. And finally, that the higher is the number of the short paths that pass to the vertices of our prefrontal cortex nodes, also is able to explain working memory performance, which is what we could observe with the between and centrality measure. And with this, I want to thank you all, but especially the people from my group. They have been very collaborative. We have worked very hard. I'm very proud of what we have accomplished.
Great, Arianna, thank you. Are you planning to continue?
Hopefully. I mean, we were surprised. Up to yesterday, we didn't have any results. Then something clicked, and we started looking at lower thresholds and more in details into networks and nodes. So that's interesting.
How do you comment the second result, that more short paths are better?
So I guess this is a measure of centrality of the nodes. So the more the nodes of our frontoparietal network are central in the communication of the information flow of the network, then the higher is the performance of the working memory. I don't remember if this was specific for reaction times, which would be even more interesting. But yeah, actually, yeah. See, like the centrality of the networks of the nodes of the prefrontal cortex was predictive of tax reaction time. So I guess it's a measure of how fast the information can get to the node, because it has a lot of paths that cross them.
Thank you very much.
Thank you.
Now it's time for the working group proposed by Lorenzo Pini.
Do you see the screen?
I do see the screen.
Okay. I think I was the guy with the technical issues with BrainHack. Sorry for that. So in this project, we investigated the association between the variability in atrophy and connectivity in Alzheimer's disease. And just me and Cecilia and Alessia, we were the working group for this project. Why the variability in atrophy and connectivity? We know that there is a specific trajectory in atrophy in Alzheimer's disease, which is a temporal parietal frontal trajectory, which is typical of this atrophy pattern in this disease. And we also know that Alzheimer's show an early breakdown of connectivity of a specific network, the default one network, and the aberrant connectivity of this network is linked with the amyloid deposition, so with the molecular characterization feature of this disease, and also with the atrophy pattern. But there are also several interesting studies showing that there is a great variability within Alzheimer's patients, both in terms of atrophy, this study by Osse and Koppele, and also in terms of functional connectivity. We know, for example, that Alzheimer's disease shows different clinical phenotypes: early onset, late onset, posterior cortical atrophy, and there are typical brain signature in these clinical phenotypes. So the aim of this project was to investigate the link between this variability in terms of atrophy and the connectivity in a sample of prodromal Alzheimer's disease patients. So patients with a mild cognitive impairment, but with a positive molecular profile. So these patients, these MCI were amyloid positive. And we investigated with a new method, which is termed lesion network mapping, which was developed for stroke lesion. But in this paper by Darby and Tetrold, it has been termed also the atrophy network mapping, which basically you can use the atrophy pattern of patients to build a connectivity, a common connectivity profile. So we investigated this link using this indirect method, and we wanted to assess whether the indirect fingerprint was similar using with the direct connectivity pattern. Because of time, we only focused at the moment within the framework of the indirect method. So the results I'm showing are based on this indirect data set. So what we have done in the first vein was to discuss how to extract the information from atrophy. So what we have done was to segment the structural MRI of our MCI patients, 165. And then based on the mean and standard deviation maps of the gray matter from a healthy control, which were age matched with our patients, we compute a zeta score gray matter map. And then from this zeta score, for each patient, we extract the peak of zeta score, reflecting the highest value of atrophy compared to the healthy controls. Then this peak was used to build a sphere of 5 millimeters of radius, which is an approach that is typically used for CROI connectivity studies. And then using the HEP dataset, because our patients were from the ADMI dataset, but then we used the normative sample to compute the functional connectivity from the Human Connectome project, using this CROI to compute the whole brain connectivity. We performed this approach for all patients, so for all the seed, which were coming from the atrophy map. We just use 20 Human Connectome subjects for the moment because of the computational time that requires to compute the maps for the dataset, and then we create a mean map for every patient. So an indirect mean map of connectivity. So for the first 6 patients, we just finished for 6 patients. You can see that there is a kind of variability in the atrophy pattern. For example, MCI patients 1 and patients 2 show an atrophy, the highest atrophy value in the hippocampus, which is linked with this common connectivity pattern, while patients 3, 4, 5, and 6 show a different connectivity pattern linked with the atrophy. Patient 3 show a connectivity resembling the frontoparietal network, and patients 5 the silence network and the visual network, and patient 6 the dorsal attention, while patients 4 with atrophy in the temporal lobe show a very weak connectivity maps. Then we investigated whether these atrophy maps were linked with specific structural connections. We used the toolbox of Joseph Griffiths that published this year, 2020, which basically in this toolbox, more than 800 tracks from the Human Connectome project are available. And this tool can assess using, in this case, a vision. In our project, we use the atrophy map, which
1 minute,
tracks,
Lorenzo.
Yeah, which tracks are disconnected. Yeah. And so in our patients, we saw that there is as for the connectivity for these patients, these hippocampal atrophy, a common tracks, which is linked with the connectivity pattern, as you can see from the hippocampus to the motor cortex. So this atrophy is linked with this network and with the corticospinal tracts. But there is for example, for patients 4 with not clear connectivity maps, also this atrophy is not linked with any structural disconnections, which can explain probably these weak results. While patients 5 with this salience and the visual pattern show this specific structural disconnection. So To conclude, we saw that there is a variability in the atrophy pattern in MCI patients, as the previous study suggested, and that this atrophy pattern may be linked with specific functional and structural networks using this hand-directed method. Of course, there is still an open question whether the hand-directed functional and structural networks are affected in MCI, and to answer to this question, we should use the data set from these patients. That's all.
Thank you. Maybe the picking of only one peak might not be the best strategy. Do you agree?
Yes, we discussed a lot about what is the best strategy. We use the peak for computational time, basically. But yeah, probably would be better or to use the cluster of the atrophy, which show the variability among patients, or probably, I think the best solution would be to use the parcels. So depending on the peak on which parcels, we can use that one. Use this CEDAR-Y for just for time.
Thank you, Lorenzo. Anyways, amazing results. Are we done with the groups, Davide?
No.
We have 2 more groups.
Okay. Please be quick because the speaker is already here.
Okay, group number 7 is precans proposed by Cristina, Enrico, and Massimo. Is anybody from this group here?
Unfortunately, Cristina Scarpazza cannot be here today, so I'll try to substitute her. And can I share the screen? Yes. Here it is. Can you see the screen?
We do.
Okay, here it is what we did with the group. It's a first draft for the PECANS or the PRINCANS, which is a checklist and guidelines for how the studies in cognitive or in cognitive psychology or neuropsychology should be reported or should be evaluated. What we prepared is a first draft of the checklist. Now there are like 120 items. They are too many, and some of them are still a little bit too general, so they have to be refined. But this is just the first draft that we will submit to the experts to try to reach a consensus through the Delphi method. Actually, Cristina is the expert of the Delphi method. It is a recursive procedure that goes through several rounds of voting in which the experts we will contact have to decide whether each of the item is important, how much important they are, and so. And also we tried to divide the items between the required ones and the recommended ones. So here are some examples which we'll go through. We divided among preliminary information. This includes the data collection, when the data was collected that could be relevant, and this should be specified when reporting the study. Whether the study was pre-registered and what should be reported if it was pre-registered, and also whether any data or code is freely accessible, and in this case, a series of specifications. And also the informations about that should be reported in the paper. This is largely inspired by similar checklists and guidelines like the PRISMA and several other checklists that are already used in the medical field, but still not in psychology. So this is the first attempt to try to propose something similar in specific for cognitive psychology. So what should be specified in the abstract? Including, for example, the effect size or the number of participants. Some of the items are obvious and they are already considered as something that must be reported, but something can be less obvious. And in any case, our proposal is that we should try to standardize the reporting. Or what should be reported in the introduction. This is, again, inspired by the PRISMA guidelines. Whether the relevant literature is reported, again, is obvious. But for example, whether the study is exploratory or more hypothesis-based than confirmatory, this is something that should be made explicit in the introduction, for example. The study type, whether it was correlational or experimental or a quasi-experiment, whether it was longitudinal or cross-sectional. This is again obvious, but it's important to report. A series of specifications about the participant. For example, here we have a lot of items, but again, this is all the proposals, and then we will have to select which are most important according to the experts. For example, the demographic variables, the characteristics, and how the participants were recruited, and so on. Also a few items about the ethical issues, and then several items about the instrumentation, the procedure, the stimuli, the specific characteristics of the stimuli, and so on. Some of them are conditional on specific studies. For example, some of the items are conditional on whether the study was cognitive or mainly neuropsychological. The design analysis, the a priori power analysis, but also other aspects. For example, how many effects were investigated, how many statistical tests were conducted, and whether this was taken into account in the power analysis, and whether it was a priori or retrospective. And a series of specifications about the statistical analysis, of course, starting with the approach, and a series of other aspects, including the effect sizes, the uncertainty indicators, the statistical software, in case it was used, which one, which packages, what should be reported about the results from the relevant descriptive statistics, and a series of specifications that are important, and what should be reported in the discussion eventually. Here we have the first working group, which is ourselves, but then we will try to include other experts as co-authors in this working group from the field of cognitive neuroscience, and also those who work with methodology and open science. This is the first step. We have already prepared and drafted also an email for them in these 3 days. And then we have set the way forward with the Delphi method to try to involve as many experts as possible for the recursive voting of the items and the eventual selection of the final checklist. So here it is, and we also set a time schedule, which hopefully will come to an end by about springtime.
Thanks, Enrico. Thank you. Very nice work. Hopefully it will lead to a consensus and a paper. What is the last one?
The last working group is the one proposed by Nicolò Trevisan.
Okay, I can share the screen.
Nicolò, super quick, please.
I'm going to be super quick. Can you all see?
But it's super interesting.
So our project was quick reminder comparing the structural brain of 29 chess masters to 29 controls. So what we did was doing structural analysis starting from VBM, studying gray matter and white matter, but this was just on an educational point of view to show how the statistic was done, preprocessing was done. The real purpose was to look at the surface analysis, and we did indeed find some results. We found some results in the cortical thickness that actually showed that the master were showing a reduced cortical thinning. This is actually interesting because it was already studied in a study published in June of this year. So we replicated the results and validate our results, especially because the real measure that we wanted to talk about since the very beginning is the cortical complexity, which we indeed find something. So to give you a brief explanation of what is cortical complexity is a way to measure how much complex is the brain. The brain is indeed complex, okay? And it needs to have a complex structure because it's embedded, it actually needs to be constrained. It's constrained by the skull. And so that's why it evolved to have a very complex form. So the idea behind of the cortical complexity is that the brain has a fractal dimension, a fractal geometry, kind of like a broccoli. So you can think the brain having the same fractile geometry, kind of like a broccoli, that you can cut it down and still has the same shape, even if you cut it down more than one time. So the idea behind the brain is that instead of cutting it down, at the level of zooming in that we can do in the brain, we can still find the same shape. And how many times can we zoom in to find the shape is the fractal dimension. This is explained very briefly for the sake of time. So this is what we analyze. This is the brain in the cortex surface, this fractal dimension, this fractal value repeated in the cortex. And we found two different clusters where the master, so the expert chess player, showed more complex brain areas. So there's those areas where this one, okay, so they're both anterior areas. These are the coordinate, the box of activation. One area was 15, the other 46. They were both significant after a FWE correction at 0.05. So we're pretty sure that there is something happening down there. And the first area is the BA47 in the inferior frontal gyrus. This area is known to be involved in language planning and semantic processing. What we did in the last hour before this presentation was try to gather some literature, to study some literature to understand why the chess expert would actually show you some differences. We found that quite a bit of studies in just a brief research. This one speculates that the region is not just linguistic for linguistic abilities. For example, you can study music in this paper, but it's also for sign language processing. So it's not just auditory modality. But again, even more interesting, the infrafrontal gyrus is active in auditory distraction tasks. So it's also involved in attentional control. And then again, there's also this interesting paper that is named The Coding of Legal Ambiguity with Neural System Getting Choices. And this is actually probably the most interesting because it talks about partial ambiguity. When information regarding reward probabilities is important for decision making is hidden or not easily obtained, the subjects must engage in a search for tractable information. So this is, I'm going to say easily, but can be traced back to the chess game. Like another studies of the 2002, this one is more famous. I think a lot of people have heard about it. It's the intentional states in competitive game. When this area, the BA47, is activated when mentalizing about this competitive game. So thinking also about theory of mind and the challenger of the game. Going to the other cluster, this one is always in the frontal pole, in the middle frontal gyrus, in the BA10. This one is involved in strategic processes in memory recall and various other executive functions. But it's also thought to contain 2 or 3 subregions that serve both functions such as multitasking, social cognition, attention, and episodic memories. All these domain can actually trace back to the chess, like multitasking, of course, keeping in mind what the moves are going to happen, social cognition, understanding the challenger, what's going on for his mind, attention, of course, keeping track of all the moves, and the episodic memory. Expert actually knows a lot of games just by memory, and they have a contest episodic memory retrieval for that. It's also active during goal-directed motor action. Again, this is kind of obvious why it's related to chess. Decision-making under uncertainty, inhibition processes, theory of mind. This is all the idea that we had at the beginning, and that's also to be a pro expert chess player. We also need to have an idea what's going on at an empathic level, an emotional level, also with other people.
1 minute.
And then we have the joint attention. So there's a shared attentional focus of at least 2 people on a third significant object, so the 2 players and the game, and the cognitive branching. So the cognitive branching is the ability to perform tasks related to one goal while keeping in memory the information related to a secondary goal. And this, I think, actually explains pretty well the chess game by itself. Now it's done. I just want to say thank you to all my group members. It was super easy to work with them, very easy. And we did a lot of work. I think we carried out like an entire search in just 3 days. It was a lot of work, but it was also very fun and straightforward. So thank you.
Thanks, Niccolò. I think it was a nice way to generate hypotheses for future studies, because otherwise it would be a lot of reverse inference there. So maybe, yeah.
No, we need to
do an experimental study on chess players in the future. Yeah, thank you.
Yes.
Georgia, is your turn.
Okay, so we have almost done. So now, welcome to Professor Corbetta. He's here. Okay. I can see him.
Ecco.
Okay. Professor Corbetta has no need of presentation, and describing his incredible, fruitful, and productive research would take, I guess, an hour. So I tried to do like a synopsis. So he spent many years in St. Louis working at Washington University. He was the chief of the Division of Neurorehabilitation and director of neurological rehabilitation at Washington University. Just to mention one of his many works, he developed the brain model of attention that has been cited in the literature more than 7,000 times. His research has been recognized with several awards, including the highly cited researchers by Thomson Reuters, based on the top 1% rate of citation in the last decade. In 2016, he decided to come back in Italy and bet on Padova. Now he's a full professor and chair of neurology in the department of neuroscience here in Padua. And he's also the founding director of the new Padua Neuroscience Center. He's mainly interested in research focused on the organization of the brain, and recently, especially during the spontaneous activity, and on the effect of focal injuries on the network organization of brain systems. He strongly believes and always emphasizes the importance of the interdisciplinary approach to get new insight in neuroscience. And I think this BrainHack represents an amazing example of such approach, such interdisciplinary approach. We have seen that in your working group, you exchange different competencies, knowledge, you use advanced methods, and I hope that this is just the first step for developing this project. So I'm very happy that is Professor Corbetta to close this BrainHack. And the title of the presentation is The Secret Life of Predictive Brains, What's Spontaneous Activity For? So welcome, Professor.
Hello?
Yes.
Okay. So thank you for the nice introduction. Thank you to you, Patrizia, Antonino, and all the coaches for organizing the BrainHack. I think, as you said, that's exactly the kind of activities. Unfortunately, we're doing it virtually, but it's the kind of activity that will definitely spur new ideas and new research. So today, I'd like to share with you kind of a new set of ideas. I'm going to need to share my screen here. Yes. Okay. Can you see it?
Yes.
Okay. So it's, I must say I'm not very ready for this presentation, okay? First of all, it's a new presentation. So whenever you give a new presentation, it's always trouble. I know that for experience. When I gave my first presentation, then I was in bed for about 24 hours because I was so unhappy about my own presentation. So, and the data were quite good, but you know, I was still unhappy when I gave it. And the title, as you see, is kind of a catchy title because the presentation is about a new hypothesis that we have developed in this manuscript that is now at bioRxives in collaboration with Giovanni Pezzullo and Marco Zorzi. And it's an hypothesis about why do we have spontaneous activity in the brain? What is it good for? We know it's there, we know that it's highly organized. And so in this 35 minutes, if I get there, I will try to suggest some new ways of thinking potentially about spontaneous activity and maybe some ideas about experiments that we might carry out. So this is an example of
Maurizio, we lost you.
We know that there is no also, it's not necessarily that is, it needs to be conscious or even thinking about something to get these kinds of patterns. And these patterns are representing the correlation between the motor cortex and the rest of the brain. So whenever you see yellow and orange, you basically get a strong correlation with the motor cortex. Whenever you get blue, you get very low correlation with the motor cortex. And you can see here, you see a great deal of interactions between the motor cortex and the rest of the brain. And you also see, if you look enough at this movie, that some of these patterns are recursive. They're not random. They can reoccur. There are states that seems to be happening. And so the question is, how do we think about this? Now, in order to think about this, we need to take a step back and kind of think how people have been thinking about neuroscience for the last 50 years or more. I would say no more like 100 years or more. So the idea that kind of the basic neurophysiological canon for thinking about how the brain works is that you basically have energy out there. It could be mechanical energy, can be photons. The heat transducer in your sensory surfaces can be the retina, can be your skin. And this generate electrochemical activity that is transferred to the brain to basically generate, to decompose this complex natural stimuli into first elementary features, and then eventually more complex representation. And of course, this is not news, is all kind of is the textbook view of how the brain builds up representation, starting from the primary visual cortex. And this is a slide, very famous slide from Hubel and Wiesel. They show how if you present a patch, a particular bar of a particular orientation, the neurons will fire. And you build the sensory representation, and you move on to build then a motor representation, an action, a choice between different actions, different decisions, and eventually you get out of the motor system with a choice. Now, the key point here is that the energy, the energy that generates activity in the system comes from the outside. It's basically the energy of the photons that hit the retina, they get transduced to the lateral geniculus, they go to the primary visual cortex, and the oscillatory circuits that are embedded in this architecture that eventually pushes the information forward. And of course, we're known for a number of years, maybe 30 years or so or more, that attention has a role, for instance, in modulating this, what is called a feed-forward flow of information processing. And of course, we also know that things like reward can modulate this information processing. But the key point is that these representations are generated by the sensory stimulus and by the motor activity in the brain. So according to this idea, then spontaneous activity reflects internal noise that facilitates forward transmission of information, okay? Now, this is important. So if I get from my sensory input transformation state to my sensory representation state, let's suppose it's just two areas, and my sensory representation state now is in a state of high excitability, that sensory input will move forward more easily than if in my sensory representation state, it is in a state of low excitability, okay? So that's what I mean by noise. The noise basically is kind of random, Poisson, and it modulates up and down randomly the excitability of the representation. And so somehow there is an interaction between the incoming volley of sensory information and the noise in the system. Now, in the last 10 to 15 years, we have discovered that this model is definitely incorrect. And I mean, there are many people, this has been going on for 20 years or so, but there is evidence that the system is actually self-generating activity, irrespective of basically sensory information or motor activity or decision or any kind of input. And I think one of the best demonstration of this, and this is really not just a correlative demonstration, but this is actually a model. So when you build the model, you know, you can actually show that actually things works that way. And this is why physicists are very important, and physics in general is a way to simplify things for us. So this is a model that people like Gustavo Deco, Randy McIntosh, Victor Girsa, and others have been working on for a number of years. These are called whole brain modeling. And basically is a simple model in which you take a brain, the connectivity of a brain, the DTI tractography of a brain, and you basically, at each one of these parcel on the cortex, you build up a node, and now you activate this node with different kind of activity. It can be spikes, can be local field potential oscillation, can be anything you want. And as a magic, kind of a magic thing happens. It happens that the connectivity basically joins all these random patterns on the cortex. These are individual nodes, each one with its own pattern, random noise. But when you put random noise together in a structure that is connected, now you have oscillation and fluctuation be generated. And some of this fluctuation and oscillation look exactly like the resting state fMRI patterns that I show you at the beginning. At the group level, you have a match of about 50 to 60% between what we call the model, which is generated, neurodynamically generated by the connectivity and this simulated neural activity, and the actually measure empirically neural activity, either functional connectivity with fMRI or MEG or EEG. So that's kind of magical. I mean, so anatomical connection plus noise appears to generate these patterns. Okay, we don't need anything else. Noise, random noise, and anatomical connection, you get about 50% of the patterns. Now, if you're anesthetized and you're asleep, these patterns are actually quite good, quite similar to what you can measure. As you're waking up and you become more aware and your cognition kind of kicks in, then the match between the anatomy and the actually empirically measure functional pattern decreases, okay? At the individual level, the match is not that great. It's about 10 to 15%. At the group level, it's still about 40 to 50%. So there is clearly something there. The other element that people have argued for this resting state spontaneous activity, well, you got learning. So you have your anatomical connectivity, these neurons, these connections are getting activated. They're getting activated over and over, maybe with the same pattern. Eventually, they become stronger, both anatomically and functionally. And so maybe what spontaneous activity is basically anatomical connection plus noise, plus some Hebbian plasticity, some homeostatic plasticity that basically weights the connections depending on the traffic. And so here's the analogy between the highway system, which is kind of a structural connectivity system, is fixed, and the functional connectivity, which is the traffic on the highways. So the functional connectivity is like the traffic on these highways, which depends on learning and plasticity. Now, however, one thing that really bothered me for many years, and I've been trying to write this review for now 10 years, then I finally met Giovanni, who is a computational neuroscientist, and Marco, and we kind of been able to. One thing that bothers me a lot is that things like dreaming, okay? When you're dreaming, you basically don't have any cognition active, you don't have any top-down control, you don't have any decision-making going on. You just have random activity in your brain that is percolating through your connections and is creating very vivid, very amazing representation. In your dream, you can decide, for instance, to jump into this highway and start swimming or not. You make a decision. When you're falling, everybody has the experience that you're flying or falling. You can anticipate the consequences of your fall. So you're doing forward motor predictions. You meet people on the clouds or on a train or maybe in some labyrinth or something, and you make very complicated judgment about these people. You say, well, can I trust this person? Do I like him? Can I go along with him? And so all of this very sophisticated, high-level cognitive stuff that we do while we're dreaming, we're doing it, we know awareness, we know cognition, we know decision-making, with nothing that can qualify as a task. We just do it completely as a zombie. So what that suggests is that this spontaneous activity is not just connectivity being activated up and down, but is actually coding representational content, okay? There are representations that are being driven by this noise during dream. And that is a very important hint of what's going on during spontaneous activity. Now, let's suppose that you're in bed. You just had a bad day, you close your eyes, and maybe you're not very happy about your future. You're a graduate student, says, oh my God, what is going to happen to me? There is no job, there is COVID, I cannot do my experiments. What can I do? You close your eyes and you start daydreaming about the future. There is nothing going on. There is your past experience that you're drawing upon, your memories, but you can create new circumstances. You can create new ideas. You can generate new situations based on the past. And all of this is manipulation of information, is basically done. We know apparent sensory stimulation or motor action is all done in your head. So again, that is suggesting that daydreaming is using bits and pieces of this spontaneous activity, plus maybe there are some task patterns that you're doing, active daydreaming, but that is also kind of a hint about what this spontaneous activity is all about. So we know from the last 20 years of work on spontaneous activity, there are 4 lines of evidence that suggest that the activity of the brain at rest and when you're daydreaming and when you're dreaming has actually functional significance. And some lines of evidence are metabolic, some is the nature of the spatial and temporal organization, 3, the relationship to cognitive functions, which although seems now kind of passé and kind of we give it for granted, but don't forget that we're relating cognition to patterns that are measured when people are there with their eye closed in the scanner. So we're correlating sophisticated neuropsychological tasks done in another condition, another task in another day with what's going on in your brain. That's kind of amazing if you think about it. And then the fact that there is now amazing evidence of the beautiful similarity that there is between spontaneous activity and taskable pattern. So I'm going to first review these 4 lines of evidence for you, and then I'm going to tell you a little bit about some of these new ideas. All right, so this is, as I said many times, this is my favorite slide in the last 10 years. It basically showed the consumption of glucose in the brain next vis-a-vis with the anatomy and the fuse image. This is a PET MRI system. We're working with the system in Padova to basically try to understand how the variability of glucose metabolism in the cortex relates to many parameters. And as you see there, 2% of the body weight, 20% of the energy. In a kid, in a teenager, my son, who's 16, is using 50% of his glucose is going to his brain. It's kind of amazing. Every 4 molecules of glucose, 2 of them are going to the brain. And now we also know from many, many sources, that I don't have the time to review this, that a lot of this going on is actually going, some of it is housekeeping, so changing your synapses, pruning your connection, changing your mitochondria, moving neurotransmitters down the organelles, down the microtubule, all of that, but 75% is signaling. And only of this 75% signaling, 5 to 10% is task-driven, and 95 to 90% is intrinsic, that is resting. And I'm going to tell you why this is the case. So what I'm doing right now, it seems like it's complicated, but actually my brain doesn't care. It's using only 5% energy more at most, okay? What is really using a lot of energy is to keep all the rest alive, all the rest active. Now, of this activity, and this is another argument why the feed-forward model doesn't work, of all this activity, the great majority of the synapses that are active are intrinsic. They're not the one coming from the retina, and they're not the one going down into the spinal cord. That's a fraction of the synapses that are actually using energy. Externally driven synapses, about 2% of all the synapses of the brain. If you got about 10 billion neurons, you have about 10 to 16 connections. And of this connection, we got about 1 million cables going in each eye. And we got about a cable going down, a million cables going down into the spinal cord. So if I put this into perspective of all this surface here, of the surface of the brain, take that is all the connections, it's been designed, drawn in scale. The fraction of synapses of the corticospinal tract is that little tiny red square, and the fraction of these synapses coming from the retina is that little bigger red square. The whole of it, the rest of the brain, is all intrinsic, So where all this energy going to? There's been a lot of calculation and empirical measurements, and this is kind of the breakdown of the pie of where the energy is going. As I said, about 25% is going to housekeeping operation. About 20 to 20%, 10 to 20% is going to action potential, spikes. The rest of it is basically presynaptic subthreshold activity or maintaining resting potential. And I think this is very important to think about, that then we activate the brain, we're actually activating a fraction, a small fraction of all the synapses that we're using. And why? Because spikes are very expensive, metabolically are very expensive. If all our brain was actually functioning in spikes, we would run in overdrive in terms of metabolic consumption. We got a fixed metabolic budget, and in order to use this budget wisely, we need to activate very few groups of neurons at the time with spikes. Most of it is actually fluctuating in low frequency. And I'm going to tell you a little bit about the low frequencies. But what is most interesting, and I'm not sure this is going to qualify for cortex because the calculation have not been done, but it qualifies for the cerebellum based on some recent calculation, is that if you look at the circuit in the cerebellum, which is here on the left, the cerebellum is made of fibers going into the cerebellum. You got Purkinje cells, they're big mamba neurons, they're basically connecting different parts of the cerebellum, and these big neurons are projecting out the cerebellum into the thalamus. So you basically have input, you have output, and you have intracortical, intracerebellar processing, okay? And when you go and look at how much of that energy is used in doing this, reaching for a pencil and manipulating my pencil online, only 20% of my energy is actually used to do this. My output is only 20%. 82%, or whatever, I guess, 82% is maintained in what? In maintaining the potential to do other actions. In other words, is to maintain possible sensory motor plan ready if I need them. But right now I don't need them. The car is ready to go, and only 20% is used for what I'm doing right now. That's an amazing insight, that most of the energy is maintained in the potential of action rather than the actual action. And we know this, we have known this since the early stage of PET scanning, because this is a picture that people, they keep discovering kind of the same thing over and over. But if you are like me with some years on my shoulders, and I've been in this field for about 30 years, one of the amazing picture in the first paper that came out in 1985, the first mapping of the visual cortex done with PET scanning by Peter Fox in St. Louis, was this, that if you flash a 40 hertz, 10 hertz checkerboards, full field checkerboards, this is an amazing stimulus. It makes your head cringe, you got headache, your eyes are hurting, is boom, 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 10 hertz reverse checkerboard. This is the PET scan, oxygen 15 label water, that is basically mapping blood flow. That you're getting the little tiny red dot in the visual cortex. That's the control scan, in which you're basically sitting at rest in the eyes, in the dark, with your eyes closed. You see that the brain, most of the brain, doesn't care about the flashing checkerboards. Most of the brain is doing what it's supposed to do, just doing nothing. The changes in the visual cortex are those tiny changes, not that tiny, about 30% blood flow change in primary visual cortex with this mambo checkerboard. But if you start presenting more ecological stimuli, faces, words, and you start marching up into the brain, now the changes in blood flow become only 1, 2, 5%. And the change in metabolic rate of glucose is even less. It's like 1 to 2%. In fact, that mismatch between oxidative consumption and blood flow is the basis for the Bolt signal. The Bolt signal, when the brain is activated, you got too much oxygen in that region, and this is what we're detecting with the magnetic resonance imaging signal. And I'm going to show you this with this, again, this is a Siemens 1.5 Tesla vision scanner. This is my brain, in fact. And I'm looking at a flashing checkerboard, and that's the T2 star signal that we were measuring in that, and the checkerboard was going on, off, gone, off, on, off. And what you can see there, that my T2 star signal in the primary visual cortex does not move a bit, is about the same, okay? And only if I'm zooming in and I go in and detect 1 to 2% changes in oxygen, the oxygenation, I can see the classic on-off pattern. But pay attention to this fluctuation, the seesaw pattern that you see on top of this very high baseline, which is the basic metabolic rate. Those fluctuations, the intrinsic fluctuation of the brain, are actually as large, many times larger than the actual flashing checkerboard that is actually driving my brain. So this low frequency fluctuation with Bolt are occurring very slowly. And many people disregard this fluctuation because they're occurring with a cycle of about 1 to 1.5 every 10 seconds, 0.1, 0.05 hertz. And when people reported these results, neurobiologists and neurophysiologists said, well, that's just junk, okay? It's just metabolic junk. This is not neurons. Neurons work in milliseconds, okay? Tens of milliseconds, hundreds of milliseconds. This is not neurons. But as we start recording, not from single neurons, like we've done for 25 years, measuring extracellular potential, but now we're measuring hundreds of neurons with NeuroPixel, measuring everything from DC all the way to kilohertz resolution, you will see this, that at any level, at the level of calcium imaging, at the level of local field potential and the level of EEG and voltage gated signal, we see this very slow fluctuation that actually are the majority of the signal in the brain. And why is that? Because low frequency fluctuation are very inexpensive, because you're not switching on and off your potassium pump and your sodium pump very quickly like you have to do with spikes. You're doing it very gently. There is time to recharge your potential very slowly, so it costs less energy. You're using less ATP. This is why the brain is using low frequency activity most of the time. Occasionally is also using high frequency activity, but that's very rare because it's very expensive. So, and these are the fluctuations that we see with Bolt. And now I'm going to tell you, I told you about the first reason, the metabolic reason why spontaneous activity is important, because it costs a lot of energy and is the majority of the energy of the brain. Now, I'm going to quickly skip through the spatial and the temporal organization because everybody here presumably is very familiar with this data. The noise is organized in terms of space and time. Space, we get this beautiful, what we call resting state networks, which again, this seems like expected or now kind of natural, but think about it. Everybody of us got a set of 10 to 15, at this particular resolution, and these networks, everybody got the same. Who could have imagined that our brain, all our brains across thousands of individuals have this very beautiful functional architecture. That's an amazing insight. That's an incredible insight of functional cognitive neuroscience in the last 20 years, that we have this incredible functional scaffolding that is mediating whatever is going on in the brain. And of course, this network that we see with these kinds of analysis over tens of minutes or 20 minutes, a static network, of course, we know they're dynamic. Okay, so this is a dynamic state analysis done by Chiara Favaretto in my lab, and basically shows how basically these static canonical networks are basically fluctuating, and there are sub-networks over time that are developing. And of course, this has functional implication, because out of the Connectome project, 1,200 subjects that were scanned with resting state fMRI fall off this very astounding organization. First of all, this tripartite sensory motor organization, where you have visual, auditory, speech, it goes together, and somatosensory motor. And then you have these two axes of internal and external areas dealing with external information, attention, decision-making, and internal information, memory, self-reflection, perspective-taking. And why is that? Why the brain, in a data-driven decomposition way, should be organized that way? That's also another amazing principle. And of course, this principle has now been refined with arguments that these large-scale gradients of organization are not actually only present in humans, but they're present pretty much in all the mammals, okay? From very small mammals all the way to primates and all the way to monkeys. And so this is work by, for instance, Daniel Margulis that I highly recommend. This is a very nice thick review. It basically shows how this gradient, they have on one hand of the organization, we got this tripartite sensory motor structure. And on the other hand, we have this very internalized default mode network. And in between, we have all these cognitive control, frontoparietal, dorsal attention, ventral attention, salience network. They're mediating the flow of information processing in the brain. All right, so that's the spatial organization. Everybody knows that. The temporal organization may be not as known, okay? We published almost now 14 years ago with Dante Mantini an analysis in which we show for the first time that this resting state network had very specific time frequency signatures. So here, different areas of the default mode network, they seems to show on the left a peak in the Ball signal, okay, in the power spectrum analysis. And on the other hand, on the other side, we see that, I'm trying to, because I don't see my, I'm sorry. Just gonna close this, I'm gonna reverse this. Okay, we see that, for instance, the default mode network correlates with EEG power fluctuation recorded simultaneously in the alpha and the beta band, similarly to the attention network, while other network, for instance, more anterior network, they're actually ticking at different frequencies. So this was evidence that low, slow power fluctuation of the EEG signal relates to the spatial network that we see with the fMRI. If we go at a higher spatial resolution, this is work done in collaboration with Hacker and others at WashU. Here we have subjects that have been recorded with ECOG, and you see that basically you have the fMRI fluctuation on the left. Again, slow fluctuation of the fMRI signal. You have the power of the ECOG signal in the alpha band, and you see that there are power fluctuation in the same with the same frequency content. And now you see a correlation map between the resting state fMRI seed and the ECOG seed, and you see the similarity of those two seeds. Again, demonstration that low frequency fluctuation are corresponding. There are also interesting differences, and people now are paying attention to this difference because it appears that this network, they don't tick all at the same way. Sensory motor network, visual network, somatomotor network, attention network, they seems to have peak in higher frequency, So this is, for instance, you see here PT5, you see that the regions of the dorsal attention and the sensory motor network, they have peak of activities in blue and cyan that are actually in the alpha band, while activity in the default mode network in blue in the matrix, FPC and DMN, they tend to have a peak of activity actually in the theta band. So there is a differentiation between some networks. They seem to oscillate a slightly different frequency. And this is a picture of some of these results. So the node here for the correlation is in the primary motor cortex. And you see that, yeah, there is a motor network, right? This is ECOG data at 0.7 Hertz. But of course, you see that there is a lot of interaction between this particular node and the prefrontal cortex, both ventral and dorsal. And I'm not showing you medial data, but it's the same, and the same is with the basal ganglia. So the same picture that we see with the fMRI, we also see with the ECOG. So the point to take home here is that there is a spatial organization that is fairly stereotypical, that is low dimensional, and there is a temporal organization that is slow, with fluctuation in the order of about 0.1 up to 1 Hertz in terms of the frequency content. Now, the third argument for why spontaneous activity is important is that it is behaviorally relevant. I already said my surprise in finding this correlation, and I want to point out in 2 slides something that, again, is important to remember. We got correlation with very large-scale behavioral components, and here is an example, probably the most powerful example. Out of the 1,200 connectome subjects, which were studied extensively with a very deep neuropsychological battery, one component accounted for about 17% of the variance, 17% of the variance across 1,200 individuals, all right? The component loads on, in a positive way, on many tests of crystallized intelligence, fluid intelligence, spatial working memory, life satisfaction, good health, higher socioeconomic status, higher education, and on the low end, with the opposite, low crystallized, low fluid intelligence, drug addiction, low socioeconomic status. In our society, I'm not saying that this is good and bad, in our society correspond to an axis of very successful people and people that are not as successful. And that falls back onto a canonical correlation structure that is unimodal. A single component in the brain accounts for the great majority of this variability. For 90% of this behavioral data, we have here on the right in C, the segregation between task positive and task negative network that were found in the data-driven analysis of the Connectome project, also differentiate in this very large-scale behavioral component between people that are successful and healthy and lean and people that are not as successful, okay? That's amazing. If you think it's very Darwinian as an idea, that if your brain is well segregated, we don't know whether it is the effect or the cause, of course, is a correlation, but if your brain is good segregated between task positive, task negative, your life is better. That's kind of scary, kind of a scary signal. However, we also see changes in spontaneous activity in very circuit-specific circumstances. Now I'm training an area in V1, a particular quadrant in V1 on a very specific test that people have never done before. I can find that my correlation between regions in visual cortex and between control regions and visual regions, right, on the right side, they tend to change my spontaneous activity after the practice of the task. When people learn, they become practice on this task, their connectivity has changed. And that correlates not only with their change score, how well they're learning, but even it predicts before the task is performed, whether they're going to be successful or not. So if you have good integration between your visual areas, as you can see there on the right, if your visual quadrant are well integrated, you're going to be better on this task. If you are relatively decorrelated with your control region, you're also going to be better on this task. Okay? So again, this is how your baseline functional architecture is taking charge and is getting modulated by this task that is not only predictive and changing with your learning, but is also predictive of your learning. All right, the final thing that I like to point out why this is important is the fact that both, again, at the level of networks, at the mesoscopic level of circuitry, and even at the level of single neurons, there is good evidence now that spontaneous activity and task evoke activity are very similar. So on the left, you see a very famous paper by Smith et al., PNAS 2009, replicated recently, Scientific Reports 2018, where they basically show that the visual network that you find in rest, you also find in a bunch of different visual tasks, and so on, for the motor system, the attention system. In top right, you see a very famous paper done with calcium imaging, voltage-gated signal. This is intrinsic optical signal, where you see the spontaneous activity in the primary visual cortex when the mouse, the cat, is in the dark, and the activity generated by flashing bars that are oriented, which seems to be one of the features that everyone cares for. And you see that both the temporal structure as well as the spatial structure, which is shown here, shows high similarities. So the spontaneous activity seems to be replaying in the dark patterns of task activation. So there is a similarity at the map level. And finally, at the bottom right, the famous replay sequences in the hippocampus, where you have a mouse and you're recording place cells that are being fired in a particular sequence. You see that when the mouse is running the maze, the cells are activated in a serial fashion, but this particular serial set of activation, this is spikes and also oscillation, they are gated by the theta rhythm in the hippocampus, can appear spontaneously when the mouse is sleeping before the sequences run, before the mouse ever explored the maze, and after the mouse has practiced on the maze, when he's sleeping the night after, we see the same sequences. So what does this tell us? Well, afterwards, it's telling us that the mouse is somehow consolidating what is learned, replaying what he has just done during the day. But before, what does it say? It says that your spontaneous activity somehow is set up in a way to allow you to do the sequence while you're doing it. So it's a kind of an anticipation of what's going on. Okay, so in summary, what I try to tell you so far is that spontaneous activity consumes the majority of the energy budget, and it is predominantly slow. 2, spontaneous activity is organized in space and time. 3, spontaneous activity correlates and predicts behavior. 4, spontaneous activity resembles task-evoke activity at the level of network, circuits, and cells. The current hypothesis about spontaneous activity is that regards noise plus anatomical connectivity. B is some kind of an homeostatic signal gated by Hebbian functional plasticity. But as I said at the outset, I don't think that this explanation account for what we can do during dreaming, and also they do not account for some of the results that I cannot show you right now. So what can it do? All right, so one idea that we thought was helpful to explore is the idea of predictive coding and generative model. This is something that Antonino is working on in the case of decision making. Many people, is very famous, the Friston free energy model, etc., etc. So I study attention, so I know a little bit about attention. So attention, you can have basically bottom-up processes. You see a Coca-Cola sign, you feel like you want to have a Coke, or you see a burger sign, you want to go to McDonald's, or now you're hungry and you're thinking about a burger. And so that's your top-down set that drives you to your behavior, okay? Now, this interaction, according to feed-forward and feedback model of the visual system, which I would think are still dominant in the literature. This is exactly how people like Sabine Kasner and John Mansell and Bob Desimon think, is that basically what you have both bottom-up processes, feature analyzers, okay, bottom up in blue. They're being coded in bottom up saliency maps. And the saliency map are interacting with top down saliency map, behavioral goals. And this is the interaction between these processes during a task that is basically moving the subject's eyes to the particular target. Okay, it's a competition, it's a winner-take-all competition between bottom-up processes and top-down. And the top-down processes are modulating this activity. Now, in Freestonian or other kind of Bayesian inference model, what the top-down is supposedly doing is generating prediction at each one of the levels in the cortical hierarchy, is generating prediction, and the activity that is coming from the sensory systems, so the visual evoke activity, the feature-specific activity, the object-specific activity, all the stuff that has been recorded for the last 30, 40 years are basically prediction error, errors between your prediction, what is coming down from the hierarchy from the top to the bottom, and what is coming up the hierarchy from the sensory surfaces up to the brain. And it's basically this ongoing conversation between top-down prediction signals and bottom-up error prediction that are basically adjusting your behavior to let you land on the right object in the visual scene, okay? Now, this stuff must be happening very quickly because, of course, you know, we can move eyes every 200 milliseconds. And so this is a pretty fast kind of recurrent interaction, which I think is probably too fast for the kind of behavior that we do. So this idea of prediction signal is being implemented computationally in these hierarchical multi-level networks, where you have on the one hand, number 7, you have the sensory input, you have a quasi V1 visible layer, and then you have a bunch of hidden layers that are basically taking the input from the visible layer and transforming it into a higher level representation that is basically coding 4 different objects, okay? By the nature of the convergence of the connectivity that you see, the high level representation, they tend to be more complex and lower dimensional than the lower level representation. In the visible layer, you can have all sorts of patterns. In the higher level, you tend to have a combination of input, okay? And of course, this is being implemented. There are many models that implement this kind of deep learning hierarchical model in the visual system. So here is an implementation of this kind of network in the visual system. On the right side, you see a lot of association areas like in inferotemporal cortex, that maybe they're doing prediction, and you see these signals are going back one step at a time at earlier and earlier level, and then you have signals marching up the hierarchy from the retina to the lateral geniculate, converging on V1, V2, V4, and so forth. So this is what happens during a task. But let's suppose that now there is no input. Your eyes are closed. And what is all this machinery supposed to do? Well, here's an idea. One idea is that this machinery continues to generate prediction, okay? It continues to generate prediction. But this prediction now, in the absence of sensory information, they do not have any prediction error. The prediction error is basically 0 because you're at rest. You're not doing anything. You're close eyes, you don't see anything. So the prediction error is 0. So the prediction they keep approximating, they keep basically developing new prediction. And by the fact that this prediction are basically cycling mostly in high level representation with no prediction error, they're becoming compressed, okay? This is what in computational term, maximization of entropy. You're basically maximizing the possibility that your representation high level can predict any pattern because it's basically continuing predicting itself, okay? So the idea is that perhaps what's going on in spontaneous activity is that spontaneous activity is the neural implementation of these low-dimensional generic priors that correspond to the transition between low-dimensional states of prediction, okay? So, and how am I gonna show you this? So the idea is this, that if I'm looking at a cell in a slice, this is basically random activity in a slice, but now that this activity is being embedded in a hierarchical anatomical system, with learning and during development, the system is basically becomes a prediction system, not just predicting when you're acting, but also that you're predicting also when you are at rest. And I'm going to show you a YouTube video here because I like to give you an idea of what this representation may look like in your brain if you had the possibility to look at your own brain while you're doing that. So this is a flock of birds. Can you see it?
Yes.
Antonino?
Yes, we can.
Okay. So as you see this flock of birds here, first of all, they go together. They're highly correlated. And they form shapes. And these shapes are not any shape. There is a small number of shapes that have been formed. And of course, the shape, this attractor dynamics, this particular way, first of all, is a system that is very sensible to change. Okay, any small change can produce large change in the conformation. And of course, from a relatively small number of configuration, you can pretty much go anywhere. Okay, that's kind of the beauty of this. The beauty of this is that basically you can reach any point in the system starting from a very simple representation. So here's the idea that we are kind of pushing forward in this review. That basically, and this is kind of an approximation or a refinement of something that I've been saying here for the last few years, but now we have a computational framework to scaffold this idea. So when you have basically a visual stimuli and you're processing information in your visual cortex, you have all sorts of activity in the brain. This is during development, for instance. This activity will lead through statistical learning to pattern of spontaneous activity. And the pattern of spontaneous activity, for the reason that I told you, given that at rest, the spontaneous activity tend to maximize the entropy, that is the number of explanations that you can provide, the spontaneous activity becomes low dimensional, particularly in high order regions. Now, the spontaneous activity is not just connectional, as we're discussing, but the spontaneous activity is also representational. In other words, representation that are representing particularly aspects of the stimuli that have been seen before. Now, the idea is that the stimuli are not coded individually as exemplar, but the stimuli are actually in a space, okay, what we call a dimensional space, a small dimensional space in which what it counts are the latent variables in which the stimuli are represented, okay? So this is like doing a multi-scaling analysis or a principal component analysis of all the possible stimuli that you have done, and that those dimensions, whatever they are, those small number of dimensions are the ones that are basically being coded both in terms of connection and in terms of representation in your spontaneous activity, okay? I hope that was clear. So we have two kinds of prior. We have a representation prior and we have a connectional prior. I think I'm running very late here. It's for 5:15, so I think I need to, we're way over budget, but I need to wrap it up. But I want to give you some example of what I'm talking about. The first example is from Monkey IT, where for many years we thought that there were neurons like Jennifer Aniston neurons that were specific for specific phases or specific stimuli. That leads to a computational nightmare because we cannot have too many neurons, so many neurons to code billions of possible stimuli. But recent work by Chang and Cao, a beautiful paper that I highly recommend, shows that basically you can code with about 200 to 300 neurons, you can code thousands of stimuli, thousands of phases. And this is done by basically coding the distance between a few set of latent variables. They can code out of 200 neurons, 50 principal components. And with the combination of these 50 principal components, you can code predictive coding of about 2,000 phases. So this is an example of what I'm talking about. This is actually task-driven activity. What I think is going on is that these 50 components are actually coded in the spontaneous activity of the brain. Here's another example of low dimensionality. Chris Gregorti et al. Activity in infratemporal cortex in humans can be coded in one axis that is basically coding for inanimate versus animate objects. Of course, there are all the little details, but the highest level, you have a latent variable that is coding for this thing in cortex. Semantic representations in inferotemporal cortex, posterior parietal cortex, prefrontal cortex, work by Gallant, Uth et al., showing that thousands, tens of thousands of words or scenes or pictures can actually be coded in a relatively small number of semantic components whose combination that defines individual stimuli. Motor cortex, I don't have the time to go through this. Okay, I'm gonna skip this because it's a little complicated to explain, but I wanna go to this experiment because this experiment, which is a science paper 2019, really captures what I'm talking about. This is basically 10,000 neurons recorded simultaneously from mouse cortex everywhere. The mouse is sitting in the dark, not doing anything, okay? Is moving his whiskers, is moving his face, is doing his little things, okay? The movement of the mouse face can be represented by 3 principal components that explain 80% of all the movements. 3 principal components explain all the mouse faces. In the motor system, these are called muscle synergies or motor synergies. Then at the bottom, you see this raster of activity. Each raster is 1,000 neurons that are being recorded simultaneously. And you see this wave of activity, right? These bars of black activity, which are basically neurons firing together across cortex. The whole brain is doing the same. Now, the purple dotted line is the first principal component of the neural activity. In the dark, the mouse is not doing anything, it's just sitting there. The first principal component of the neural activity. You see the fluctuation? The fluctuation is 1 fluctuation every 10 seconds, which is exactly what the Bolt signal is about. And now you see in green, the principal component of the behavior that the mouse is doing. And you see how beautifully the component of the behavior in the motor cortex is feeding what's going on in the visual cortex. So motor synergies, spontaneous motor synergies, hold on a second, they just knock on my door. Come in. Yes, ho bisogno di un po' di tempo. Okay, I'm just giving a lecture. Okay, so motor synergies are basically being represented in low dimensional pattern in the visual cortex. So this is exactly the neural implementation of this idea. Okay, I got other data to discuss, more examples. You can read the review, I guess. I think we're running late, and so I need to complete this. I guess I want to kind of just say that I think these kind of ideas solve the homunculus problem and solve the problem of who's in control of whom, okay? I mean, basically, I'm just going to say something completely heretical for what I came from. Now I'm more and more convinced that something like attention as a concept probably does not exist in the brain. Attention is nothing else than 2 flock of birds. These are 2 motor sets, 2 sensory motor sets that have been set up by the task. They're just sitting there in the brain, and they're sitting there in the brain, and now you have a tiny change in the sensory stimulus, maybe a flicker on the screen, a tiny change in your eye position, a tiny change in your reward signal, anything that basically changes the dynamic of these 2 large, widespread components that we call task sets. And so there is no control. And the control and the sensation of volition is just a background. It's just an echo of your neural machinery going on. And basically, this is what maybe what's going on in the brain. We got basically this beautiful, highly representational map and connectivity maps that are basically prone and ready, primed for behavior. Now, if that is true, of course, that allows us to decide to describe why we can select an apple from an egg. You know, we look at the egg, we thought about the fact that we ate egg this morning. The egg this morning, there is an odor in our memory that just slightly biases our egg representation. Boom, the egg prior and system is activated. The same explain why it's so difficult to stop bad habits. Why? Because when you're smoking or you're doing drugs, it's not just that you're out of control, which is kind of what people or educators are saying, you know, use your control, think slow, don't think fast, all of this. Well, you're just smoking because everything in the environment tells you to smoke. It's a habit. It's a sensory motor pattern, you know. And so in order to quit addiction, people are sent to Canada in the forest, cutting trees, feeling cold, away from the square where they've been getting their drugs, because you need to change the whole pattern. And the same is with reading and piano playing. So in a way, maybe we can think, and now I'm thinking very big, that education is not practicing your control, but education is just in training good sensory motor sets in your brain to basically develop a repertoire or good, ecologically valid, survival, successful plans that basically will get activated as you're going through your life, and they will become stronger as your life proceeds. Same with racism. Racism, I don't think is, you know, it's cultural. I think is biological. Babies, they look at mom's face more than dad's face. So they're not really racist for dads. They like their moms better at the beginning. And they look at people of the same ethnicity more than people of a different ethnicity. So the brain basically, you know, is afraid of news. And so he likes to use his priors. And so again, racism unlikely will be done by cultural lessons or, you know, education. It will be done by basically mixing kids in school of different race, of different ethnicities, a different background, because basically you need to adapt sensory motor sets. Okay, so these are some of the conclusion. Spontaneous brain dynamics are manifestation of top-down dynamics of generative model detached from action perception cycles. Generative models constantly produce top-down dynamics, but we call them expectation and attention during task engagement and spontaneous activity at rest. Spontaneous brain dynamics during resting periods optimize generative model for future interaction by maximizing the entropy of explanation in the absence of specific data, reducing model complexity. Low frequency brain fluctuation during spontaneous activity reflect transition between generic priors consisting of low dimensional representation and connectivity patterns of the most frequent behavioral states. High frequency fluctuation, I haven't really covered this, during spontaneous activity like in hippocampus replay may support generative replay in model learning. We haven't really talked about this. Okay, so I will stop there, stop sharing my screen. I apologize for the delay. I'm sorry, it was a long talk. As I said, it's the first time that I give it. And so if you have any question, fire away. The paper has not been published, so there is time to revise it even significantly.
Thank you, Maurizio, for your terrific talk. I hope to be unprepared as you are in this presentation. So great talk. Are there any questions from the audience? You can also chat. Okay, so Francesco asked, thank you. I didn't understand if the transition between low dimensional priors of spontaneous activity could occur in anticipation of some known future demand. For example, if I know that I'm going to do something in 5 minutes, could this trigger a miserable change in my priors?
Yeah, I mean, in the paper there are, I mean, this is a theory, of course. You got tested and we have to deny it. So, I mean, we have to refute the theory. Yeah, the idea would be that basically, you know, we talked a lot about space, spatial connectivity and spatial representation. There is a contextual temporal representation. So if and this is why I think, okay, now I'm becoming philosophical, but anyway, but this is why context is very important. So I think one of the experiments that would be nice to do is to say, let's suppose you're doing like a face recognition task or a scene recognition task, and now you know in advance which one you're going to do. Well, I would expect that your face prior would start getting going. And we don't know whether that is going to help your face perception or hurt your face perception, but certainly we know, and this is a paper that I skipped, but there is a paper in which we show that this prior and visual cortex, they're really exclusive along these two dimensions, animacy, non-animacy, that I described, that Chris Kegorda has described. So if you have a phase prior in your visual cortex, your scene prior actually is not coexisting at the same time. They're kind of doing this a little bit. And so, yeah, so I would expect that there would be that kind of contextual effect on the prior, yes.
Maurizio, thanks for this great talk, very interesting and inspiring. It would be interesting to somehow test all this theory developmentally to try to grasp more the role of experience in shaping these patterns.
Yes, I think that would be yeah, there is one of the slides that I skipped is this paper by Berkes, Science 2011, and they're recording ferret visual cortex, and they're recording it spontaneously during the presentation of artificial stimuli, synthetic stimuli, or natural stimuli, and they're recording it in infants ferrets and adult ferrets and during their development. And something that happens, which is very interesting, is that the prior in the infant are not very good. They're kind of very diffuse and general, and there is not that much difference between a natural stimulus and a synthetic stimulus. But as you're going up, and we see this also in our human data, and we see it in the motor system, we see it in the visual system, as you mature, your prior are getting tuned to your natural stimuli in shape and frequency, and the random stimuli, then they're very different. They're generating many more prediction error. So the prior is actually much more similar to the posterior for natural stimuli than the posterior for random synthetic stimuli. So what you're predicting is exactly what Berkes and others have shown in the ferret's visual cortex. That was a science paper.
Thanks.
Other questions? Okay, no, I like your provocative idea of the absence of attention, or the other old concept belonging to cognitive science. And I think this could be the key to reconciliate personality, cognition, and other psychological constructs. So personality might be sensory motor patterns acquired during the life to cope with environment, has cognitive styles or other dimensions.
Yeah, I think that would be, that's a good idea. I mean, I think I like that insight that you're having, is that would be to be tested in, that would require some kind of an extensive, probably psychological study testing kids at different ages, and then look for correlation as you're doing maybe in between, say, cognitive skills and maybe personality, and maybe the development of an obsessive compulsive or a neurotic, maybe got some relationship with the way you're dealing with, your stress level to sensory stimuli or other things. So that's definitely worth exploring. Okay.
Okay, thank you.
Good. Yeah, thank you. And congratulations again, the BrainHack. I heard it was really good. So.
Thanks, Maurizio.
Ciao, ciao a tutti.
Ciao.
Okay. So we are almost done. Antonio, Patrizia, Davide, do you want to say something?
I want just to say something because I couldn't stay all the time here, and it's a pity, but I was busy with other duties. But I want to remember that this is the third year that we are doing it in Padova, and I think it is a very good idea. And I thank very much the organizer, also Michelle, that I didn't see here today, Davide, Antonio, and Georgia, that realized it also this year. And I hope that we will do it again next year, because I think it's really very, very good one. It's a pity that everybody is full of things to do and we can stay all the time on, but young people maybe has much more time than I have. And I hope that there are other occasions to talk together. I didn't want to make any intervention in Maurizio Corbetta's speech because I had so many questions that we could stay here till the night, but I think it's enough for today. We will have our meeting together. And I think that also between the other people here, we can have our meeting to speak about how brain is working in a very, very large way. So thank you to have worked with it. And also thank you to all participants that I heard some of the little groups proposal quite interesting. And so I hope that they are going on and have more data. So thank you very much to everybody.
Thank you, Patrizia. I also would like to thank everybody for this nice event. The contribution of everybody was key for the success of it. We only miss a little bit of social interaction, unfortunately, this year, but this is, of course, understandable due to the pandemics. So I hope next year we can do the same, but in presence with a lot of spritz and you know, talks and evening together, etc. So thank you very much.
Yes, it was a challenge at the beginning, and we didn't expect the final result. So I have to say that I'm really satisfied by these 3 days, and I hope you are as well. And please tell us some feedbacks or if you have any, I don't know, questions, you can email us. And thank you all for your contribution and your participation.
Okay.
Do you want to say something, or we can say goodbye? Or if any of you wants to share your experience or some thoughts, please be free to speak.
Yeah, even later, if you have feedback on this event, that would be very welcome. Yeah. I guess Davide is silent because he's choosing the music to close the event.
Nope, I'm not. Enough for DJing. No, I was just thinking about after we stop recording and live streaming, why don't we stay here just a bit and show the face for like a group photographs or something similar, if we can.
Yes.
Okay, I'm just stopping to recording the video in 3, 2, 1, and you just stop and stopping.